In this video, we will discover the essentials of microservices, dive into monolithic architecture, and explore its key characteristics. Microservices, you imagine transforming your complex applications into a well-orchestrated symphony of small, independent services. This is the magic of microservices. Unlike monolithic architectures that bundle everything into one giant block, microservices break down your system into agile pieces that communicate seamlessly through APIs. This design pattern not only boosts agility and scalability, but also simplifies the maintenance of complicated applications, making it a game changer in modern software development. So, if we take a look at monolithic architecture, think of monolithic architecture as building an application from one solid block. All parts of the app are tightly connected and run together on a single platform. It's great for smaller projects where you need something simple and quick to develop. Let's take a look at characteristics of monolithic architecture. Imagine a classic all-in-one device where every part is built into one seamless unit. This is monolithic architecture, a single unified code base where all components like the UI, business logic, and database access, these are tightly connected. When you make changes, you update the whole device, which can be large or heavy if you only need to pull one part sharply. While it offers consistency by using a single technology stack, scaling up means boosting the entire system, which can be inefficient. It's a solid choice for simplicity, but scaling and updating can be a bit of a challenge. So, imagine a classic well organized office where every department has its own distinct role but works within a single building. In monolithic architecture, your application is similarly divided into three core layers, each with a unique function. One is presentation layer. This is your front desk, greeting users and handling their requests, displaying information and managing interactions. The other one is business layer. Think of this as the operations team, making sure everything runs smoothly by processing data and enforcing rules, ensuring that all decisions are consistent and correct. And the other one is data layer. This is your filing room, storing and retrieving data like a pro, managing everything from databases to storage systems to keep your information organized and accessible. Together, these layers form a cohesive unit where each part plays a critical role in keeping the application running efficiently and effectively. As a conclusion, in the world of software architecture, monolithic designs are like a single, well oiled machine, simple and unified, but challenging to scale and update. Microservices, on the other hand, are like a collection of specialized tools, each working independently yet seamlessly together, offering agility and flexibility for complex applications. Whether you prefer the streamlined efficiency of a monolith or the modular sophistication of microservices, each has its strengths for tackling different challenges in the tech landscape. In this video, we are gonna talk about microservices story. According to our story, we have a pizzeria store in Decoupled City. So, let's begin. In Decoupled City, pizzeria store was famous for its efficient and delicious pizza, thanks to its unique microservices approach. So we have some key players in this scenario. Lucy, the order manager, routed all orders to the right departments. Tony, the dough master, crafted perfect dough bases. Carla, the sauce and topping maestro, added delicious flavors. Bruno, the baking expert, baked each pizza to perfection. Sam, the delivery pro, ensured pizzas were delivered hot and fresh. So, when the big corporate order came, Lucy coordinated seamlessly with Tony, Carla, Bruno, and Sam. Despite the complexity, they handled it smoothly, showcasing their microservices approach. So we have some key points from this story. One is specialization. Each department focuses on one task. The other one is independence. Departments operate and scale independently. Next, efficiency. Smooth handling of complex orders. Next, innovation. Inspiring others to adopt the method. And as a conclusion, in essence, my pizzeria store demonstrated the remarkable power of the microservices approach by allowing each department to specialize and operate independently. They achieved unparalleled efficiency and flexibility. This method not only enabled them to handle large and complex orders seamlessly, but also set a standard of innovation and excellence in Techville. In this video, we are going to learn vertical and horizontal scaling in microservices. Let's start with a simple explanation of vertical and horizontal scaling in microservices. So, vertical scaling, in other words, scaling up, it means adding more power to an existing machine. These are CPU, RAM, etc. There are some advantages of this. For example, simplicity or easy to implement. But there are also some disadvantages. These are limited by the maximum capacity of a single machine. It can be costly. So, if we take a look at horizontal scaling or scaling out, it means adding more machines to handle the load. There are some advantages of this. For example, more fault tolerant, it can handle more load, and virtually unlimited scaling. But there are also some disadvantages. These are more complex to implement and manage. It requires efficient load balancing and service orchestration. So, let's take a look at Pizza Villa story. So, once upon a time, in the busy town of Pizza Villa, there was a popular pizza delivery company. It's called Pizza Express. Their pizzas were loved by everyone, and as more people ordered, the system handling the orders began to slow down. The IT team knew they had to scale their system to keep up with the demand. Vertical scaling, or the bigger oven. First, they tried vertical scaling. Imagine their ordering system as a pizza oven. At first, it was a small oven that could bake a few pizzas at a time. To scale vertically, they upgraded to a bigger, more powerful oven that could bake many more pizzas simultaneously. This worked for a while. The new oven handled the increased orders well, but soon even this powerful oven couldn't keep up with the growing demand. The team realized they couldn't keep buying bigger ovens forever. There was a limit to how large an oven could be. So, horizontal scaling, or many ovens. Next, they tried They tried horizontal scaling. Instead of relying on one big oven, they bought multiple ovens. Each oven could bake a moderate number of pizzas, but together they could handle a lot more. In the microservices world, this meant adding more servers. Each server was like an individual oven, and together they formed a massive kitchen. Orders were shared among the ovens, so no single oven was overwhelmed. Finally, scaling success. With horizontal scaling, Pizza Express store could meet the growing demand without compromising service quality. Their system became more reliable and efficient, delighting customers with prompt deliveries even during busy times. And so, Pizza Express thrived in Pizzavilla City, showing how horizontal scaling can provide a better solution compared to vertical scaling, especially for handling lots of orders in a microservices system. In this video, we are going to talk about eventual consistency in microservices. So, what is eventual consistency? Eventual consistency is a consistency model used in distributed systems and databases where the system guarantees that given enough time, all updates will propagate through the system and all nodes will converge to the same state. So, there are some principles of eventual consistency. One is asynchronous updates. So, changes made in one microservice or component are not immediately reflected in other components. Instead, updates propagate over time. Next, conversions. Over time, all replicas of the data will become consistent, though this may not be immediate. Next, failure tolerance. The system is designed to handle network partitions and temporary inconsistencies with the guarantee that consistency will eventually be restored. So, we have a story here to make it clarify. Eventual consistency in microservices, the pizzeria story. So, for great customer experiences in the digital world, backend systems need to work well. Pizzeria company, it's a leading pizza delivery company in Tech City, uses a state-of-the-art microservice architecture to ensure smooth operations and satisfied customers despite the complexities involved. This story explores how Pizzeria achieves eventual consistency in its microservices. First of all, order placement and processing. Emma ordered a delicious pizza through the pizzeria app. The order service captured her details and created order with the number of 1, 2, 3, 4, 5. It then sent the payment details to the payment service, which processed the payment and updated its records. Next one is coordination with kitchen and delivery. With payment confirmed, the order service sent details to the kitchen service to prepare Emma's pizza. Simultaneously, it informed the delivery service, which assigned to order to Joe, a delivery driver. So, next one is eventual consistency in action. The notification service responsible for customer updates received messages from both the payment and delivery services. Due to a network delay, the notification service first received the delivery update and followed by the payment confirmation. Emma received notifications in this order: your pizza is on the way, and then next message is your payment was successful. This small issue with the order of notifications demonstrates the idea of eventual consistency. So, in the scenario described, the correct order of notifications should be indeed be first your payment was successful, and next your pizza is on the way messages. Next one is handling inconsistencies. Pizzeria services manage temporary problems well. The notification service fixes and reorders messages if they are out of order. Services regularly update their information. The order service makes sure all orders are paid, and the delivery service checks that pizza are ready for delivery. And finally, satisfied customer. Even with the brief notification mix-up, Emma's pizza arrived on time, hot and delicious. Temporary inconsistencies in notifications didn't affect her overall experience. All microservices eventually reached a consistent state, ensuring a smooth process from order to delivery. In this video, we are going to learn how to use microservices in e-commerce applications. So let's take a look at an example of an e-commerce application to illustrate microservice calls. So according to our scenario, user places an order. User service handles user authentication and profile management. Product service manages product catalog and inventory. Order service manages order creation and processing. Payment service handles payment processing. And shopping cart service handles operations such as adding items, removing items, updating quantities, and retrieving the current state of the cart. So there are some steps involved in the shopping process. First, user authentication. The API gateway routes the login request to the user service. After successful authentication, the user service returns a token. Next, order creation. The front end calls the order service with the user's token and order details.
The order service verifies the token by calling the user service. Next, checking the product availability. The order service checks product availability by calling the product service. Next, shopping cart processing. The cart service might use a database to store cart information, and it exposes APIs for other services to interact with. And next, payment processing. If products are available, the order service calls the payment service to process the payment. And finally, order confirmation. Once the payment is successful, the order service creates the order and sends an event such as order created event.
In this video, we are going to talk about microservices communication. Imagine you are the head chef at the bustling restaurant, but this is not any ordinary kitchen. It's a kitchen with dozens of independent chefs, each responsible for a specific dish. Your job is to ensure these chefs work together smoothly, even though they don't talk directly to each other most of the time. This is where microservices communication comes in, turning your chaotic kitchen into a well orchestrated culinary masterpiece. So, in the kitchen, you have a team of waiters who run back and forth, carrying orders to the chefs and bringing finished dishes to the customers. These waiters are like the HTTP REST calls in microservices. Each chef works independently but relies on these waiters to deliver specific instructions. It's simple and effective, but when the restaurant gets busy, the waiters can get overwhelmed, causing delays. Let's take a look at gRPC Sauce Chef. To speed things up, you bring in a team of highly skilled sauce chefs, trained to communicate quickly and efficiently with the head chef using a special language only they understand. Let's call it gRPC. These sauce chefs are faster and more efficient than the waiters, reducing the time it takes to get orders from the head chef to the kitchen. However, this system requires a bit more coordination and setup, but the performance boost is worth it. In this video, we are gonna talk about microservices workflow as a story, so we can clarify the topic. Once upon a time, in the bustling city of Techville, a team of skilled architects set out to build something extraordinary. Their vision, a grand mansion, but not one made of bricks and mortar. This mansion would be crafted entirely from code. Each room would represent a unique microservice designed to handle a specific task with precision and elegance. The journey began with the architects gathering around a large table, sketching out the mansion's blueprint. They carefully planned each room's layout. The kitchen would manage orders, the living room would handle customer interactions, and the library would store crucial data. Each room was envisioned as an independent microservice, ready to play its part in the mansion's grand design. With blueprints in hand, the architects set to work. Each took charge of their room. building it with creativity and precision. They ensured every room had its own door and, in other words, an API, allowing other rooms to communicate when needed. Despite being interconnected, the rooms were strong and independent, able to function even if another room had a hitch up. As the mansion neared completion, the team connected the rooms with elegant hallways. These hallways, representing inter-service communication, ensured smooth navigation for visitors. The architects also installed state-of-the-art security systems to keep intruders out and added sensors to monitor the mansion's health and performance. Finally, the big day arrived. The mansion was ready to welcome the world. With a grand ribbon cutting ceremony, the mansion went live. Visitors marveled at how seamlessly the rooms worked together, each performing its task flawlessly. The mansion was not just functional, it was a work of art in the world of microservices. But the architects didn't stop there. They continued to upgrade the mansion, adding new rooms, refining old ones, and ensuring it could handle more visitors. They stayed vigilant, always ready to improve and adapt. The mansion thrived, becoming a landmark in Techville, a shining example of how microservices could build something truly magnificent. And so the architects and their grand mansion lived on, constantly evolved and inspiring others. Their creation became a beacon of innovation, showing the world that with vision, creativity, and the power of microservices, one could build something that stands the test of time in the ever growing city of Techville. The story of the Grand Mansion in Techville is a testament to the power of vision, creativity, and collaboration in the world of microservices. By carefully planning, building with precision, and continuously improving, the architects created something more than just a functional system. They built a living, evolving masterpiece. This story reminds us that with the right approach, microservices can be more than just a technical solution. They can be a foundation for innovation, scalability, and lasting impact in the digital landscape. The mansion stands as a symbol of what's possible when we embrace the full potential of microservices, crafting not just code but a legacy.
In this video, we are going to learn microservices workflow, microservices deployment, and best practices for managing microservices. In microservices workflow, first client send request. Client sends a request to the API gateway. Next, API gateway, it routes the request to the appropriate service. And next, service processing. The service processes the request using its own database. And finally, response. The service sends the response back through the API gateway to the client. And how does microservices deployment? One is containerization. In containerization, we use Docker to package services, ensuring consistency across environments. And the other one are orchestration. We use Kubernetes to manage deployment, scaling, and operation of containers. There are some best practices for managing microservices. These are service discovery. We use tools like Consul, Eureka, or Kubernetes to manage and discover services dynamically. And the other one is API gateway. We implement an API gateway to handle client requests, route them to appropriate services, and handle cross-cutting concerns like authentication, logging, and rate limiting. And CI/CD pipelines, it automates the build, test, and deployment process to handle frequent updates and ensure reliability. And centralized monitoring and logging. Centralized logging use tools like ELK, Stack, it means Elasticsearch, Logstash, Kibana to aggregate logs. And the monitoring use Prometheus and Grafana to monitor service health and performance. In this video, we are going to learn comparison of microservices and monolithic architecture and also some challenges of microservices. If we compare monolithic architecture and microservices, monolithic architecture has a single unified code base. All functions such as user management, order processing, inventory are part of one application and one database shared by all functionalities. On the other hand, microservices architecture, these are separate services for different functions. Each service has its own code base and database, and communication between services can be done through APIs. Some challenges of microservices. One is complexity. Managing multiple services can be complex and requires robust service discovery, monitoring, and logging solutions. And the other one, data consistency. Ensuring data consistency across services can be challenging. Requires careful planning for eventual consistency, distributed transactions, or CQRS. It means command query responsibility segregation. And communication. More network communication between services compared to in-process calls within a monolithic application. In this video, we are going to talk about microservices architecture implementation as a story to clarify the topic. So, once upon a time, a team of developers set out to build a mighty system using ASP.NET Core. Their goal was to create a flexible and scalable architecture. So they decided to break their system into small, independent microservices. Each service would have its own unique role, like managing users, processing orders, or keeping track of inventory. First, they planned the journey carefully, defining the boundaries of each service. Each service was given its own database to manage,
ensuring they could all work independently without stepping on each other's toes. Next, the developers built each microservice as its own little castle using ASP.NET Core Web API. Inside each castle, they organized their code using domain-driven design, making sure that everything was neat and modular. Next, the team knew that some messages needed to be instant, like a call across a courtyard. So they used HTTP REST for synchronous communication. For messages that could be sent by a carrier pigeon, they used message brokers like RabbitMQ for asynchronous communication. So, the team gave each microservice its own database, ensuring that the treasures were well guarded and consistent. To help the castles find each other in the vast kingdom, the team built a service registry, like a magical map. This allowed the services to discover each other without needing hard-coded paths. Next, to protect their kingdom, the developers built a grand API gateway. This mighty gate served as the single entry point, routing all requests to right castle while handling security, logging and rate limiting. So, knowing that no kingdom is free from danger, the team prepared for failures. They implemented a circuit breaker to protect their services from cascading failures and added retry policies to keep things running smoothly even when something went wrong. The developers were wise and knew they needed to keep an eye on their kingdom. They set up centralized logging and distributed tracing to monitor the health of their services and detect any issues before they became big problems. Finally, they set up CI/CD pipeline like a conveyor belt of progress to deploy updates swiftly and safely. They also ensured their kingdom was secure with strong authentication and encrypted data. And so the developers built a thriving, resilient kingdom of microservices, each working in harmony, ready to face whatever challenges came their way. In this video, we are going to talk about how to implement microservice architecture in ASP.NET Core. So, first of all, plan the microservices. Define the boundaries. Break down your application into smaller, loosely coupled services. Each service should represent a specific business capability, such as user management, order processing, inventory, and next, database per service. So each microservice should manage its own database. This ensures loose coupling between services. Next thing we need to do, create individual microservices. So ASP.NET Core Web API creating. Start by creating a new ASP.NET Core Web API project for each microservice. Next, modular design. Organize your services into clear modules
Use domain-driven design principles to guide your structure. Next, implementing APIs. Define controllers and actions for each microservice to expose the necessary endpoints. Next, service communication. So for synchronous communication, use HTTP REST for inter-service communication. ASP.NET Core has built-in support for making HTTP requests, such as HTTP client. Next, asynchronous communication. Implement message brokers like RabbitMQ or Azure Service Bus for event-driven communication between microservices. This decouples the services and improves scalability. Next, data management. One is database per service. Ensure each microservice has its own database. Use Entity Framework Core or any other ORM tool to interact with the database. And next, data consistency. Consider implementing the Saga pattern or distributed transactions for maintaining data consistency across services. Next, service discovery. So one is service registry. Implement a service registry such as Console, Eureka to allow services to discover each other without hard-coded URLs. Next, load balancing. Integrate with load balancers to manage traffic effectively across service instances. Next one is API gateway. So one is centralized gateway. Implement an API gateway, for example YARP or Ocelot, to serve as an entry point to your microservices. It routes requests to the appropriate services, handles cross-cutting concerns like authentication, logging, and rate limiting. Next one is security. Ensures secure communication between the API gateway and microservices using HTTPS and OAuth to JWT tokens. Next, resilience and fault tolerance. One is circuit breaker pattern. Implement a circuit breaker pattern such as using poly to handle failures gracefully. Next, retry policies. Use retry policies to automatically retry failed operations. And next, health checks. Implement health checks for each microservice to monitor the application's health. And next one is logging and monitoring. So one is centralized logging. Use logging frameworks like Serilog, ELK Stack, or Azure Monitor for centralized logging. Next, distributed tracing. Implement distributed tracing, such as OpenTelemetry, to track requests across services. Next one is monitoring. Set up monitoring tools like Prometheus or Grafana to keep track of your service's performance. Next one is deployment and scaling. One is containerization. Dockerize your microservice to make deployment consistent across different environments. Next, orchestration. Use Kubernetes, Docker, Swarm, or Azure Kubernetes Service for orchestrating and managing your containers. CI/CD pipeline. Set up a continuous integration and deployment pipeline to automate the deployment process. And next, security. Authentication and authorization. Use OAuth to OpenID Connect or Identity Server for managing authentication and authorization across services. Next one is data encryption. Ensure sensitive data is encrypted both at rest and in transit. Next one is API security. Secure your APIs using JWT tokens and ensure that they are accessed only by authorized clients. In this video, we are gonna take a look at microservices project example. So we are gonna take a look at main solution and microservice solution. So we are gonna look at differences between them. First of all, we look at main solution. So this is the main solution that serves as the entry point for the entire system. It acts as the orchestrator, focusing on routing, shared services, and cross-cutting concerns without containing business logic or code from the microservices. So what does it include in the main solution? One is my company shared here. So it contains shared DTOs, common interfaces, and utility classes used across microservices. The other one is my company API gateway. So it handles incoming requests and routes them to the appropriate microservice. Next one is host project. So here it configures the API gateway. We can use Ocelot or YARP, and contracts project here defines the contracts or interfaces for the API gateway. We have domain project here. It handles domain specific logic for the gateway. So next one is infrastructure here. It handles infrastructure related concerns like logging, database access, etc. And we have service discovery here. It manages service registration and discovery, allowing microservices to locate each other dynamically. And we have test project here. So next one, here each microservice is a standalone application independently developed and deployed, containing its own domain, application logic, APIs, and infrastructure. This is our microservice project order service. So let's take a look at more deep microservice. Here we have application. Again, it contains the application services and business logic, and domain here, domain layer. It holds the core domain entities, aggregates, and domain services here. And we have entity framework core module here. It implements data access using entity framework core here. So we have HTTP API here. It exposes the application's functionality through RESTful APIs. And we have HTTP API host. It configures and runs the microservice, including middleware and dependency injection. And we have web project here. It's starting project, startup project. It provides a web interface if needed for an admin panel, for example. And we have test project here. Next, let's take a look at the difference between microservice project and main solution project. So why these are different? Because separation of concerns The main solution focuses on overarching concerns like API routing, security, and orchestration, while each microservice is designed around specific business functionalities and independence. Microservices need to be independently deployable and scalable. Each service has its own database, application logic, and APIs, which require a separate structure. And flexibility. Different microservices might be built by different teams or even in different technologies. The structure allows teams to use the best practices and tools suited to the specific service. And scalability. By separating concerns and allowing each microservice to be independently developed and deployed, the architecture can scale more effectively as the system grows. As a summary, main solution acts as the orchestrator, focusing on routing, shared services, and cross-cutting concerns without containing business logic or code from the microservices. And microservices projects, each microservice is a standalone application independently developed and deployed, containing its own domain, application logic, APIs, and infrastructure. In this video, we are going to talk about load balancing in microservices. So, what is load balancing? Load balancing is like a traffic police for network traffic. It distributes incoming requests across multiple servers to prevent any single server from getting overloaded, ensuring smooth operation and high performance. So, why is load balancing crucial in microservices? Because scalability. Effortlessly scale your services by spreading the load across multiple instances. Reliability. Keep your services running smoothly by redirecting traffic from failed or busy servers. Performance. Enhance user experience by balancing the load and reducing delays. So, how does load balancing work? There are incoming requests. Requests from users hit the load balancer. And smart distribution. The load balancer distributes these requests to various service instances using clever algorithms and efficient response. Each instance processes the request and sends the response back through the load balancer to the user. So there are some load balancer strategies. One is round robin. It cycles requests evenly across all instances. And the other one is least connections. It sends requests to the instance with the fewest connections. The other one is IP hashing. It keeps requests from the same IP address consistent by directing them to the same instance. And weighted load balancing. It allocates more traffic to higher capacity instances. So, when we implement load balancing, we follow these hardware load balancers. These are physical devices that manage and distribute traffic. And software load balancers. These are applications like HA, Proxy, and Nginx that handle traffic distribution. Cloud-based load balancers. These are scalable services offered by cloud providers. For example,
AWS Elastic Load Balancer, Azure Load Balancer. In this video, we are going to talk about load balancing story. So let's begin. We have a city, its name is Technopolis, and we have a restaurant in there which name is Bistro. It runs by robots here in the Bistro restaurant. But one day it faced challenges as its popularity grew. The problem was about the central computer systems. So they couldn't keep up with the demand and it caused delays in the services. So and the solution by Miss Ada Lovelace introduced microservices to solve this problem. So how does it work? It split operations into smaller independent tasks. And load balancer. A load balancer named Balto was added to the system. Why they added this to the system? Because to distribute requests evenly and to prevent any single service from becoming overwhelmed. And what happened? The result. The result with Balto load balancers help. So Byte Bistro's efficiency improved dramatically. Orders were processed quickly and customer satisfaction increased. In this video, we are going to learn how the Saga pattern coordinates distributed transactions across multiple microservices. By managing each step carefully and handling failures gracefully, it ensures that processes such as ordering products online remain reliable and consistent. So, the Saga pattern is a design pattern used to manage distributed transactions across microservices, ensuring that a series of operations either complete successfully or are rolled back in a coordinated manner if any of them fail. So, according to our scenario, Alice wants to buy a smartphone and accessories from ShopEase store. It is online store. Here is how ShopEase handles her order using the Saga pattern. First of all, starting the order. Alice's order initiates a chain of events across multiple microservices. The order service is the first microservice to receive the order. It records the order details and assigns an order ID. To process the order service needs to interact with several other services. So, order service receives Alice's order and starts the process. Next one is checking inventory. Inventory service checks if the smartphone and accessories are in stock. If they are, it reserves them for Alice. Next, processing payment. Payment service tries to charge Alice's card. If the payment is successful, it informs the shipping service to prepare the delivery. If the payment fails, it cancels the reserved items in the inventory service and notifies the order service to cancel the order. Next one is shipping the product. Shipping service arranges delivery. Once the delivery is scheduled, it confirms the order completion. So, how we handle failures? If any part of the process fails, for example, payment fails, the Saga pattern ensures that previous steps are undone, like releasing reserved items and canceling the order so everything stays consistent. So finally, success. If all steps succeeded, Alice gets her smartphone and accessories delivered and the order is marked as complete. So, the Saga pattern has ensured that every step of the transaction was handled in a coordinated manner. By managing distributed transactions through compensating actions and maintaining consistency, Shopee's store provides a reliable shopping experience for Alice and all its customers. As a result, the Saga pattern helps Shopee's manage Alice's order across different services, making sure that if something goes wrong, the system can fix it and maintain consistency. In this video, we are going to learn circuit breaker pattern. So what is circuit breaker pattern? The circuit breaker pattern is a crucial design pattern used to gracefully handle failures in distributed systems and prevent cascading failures. It helps maintain system stability by allowing services to detect failures and respond appropriately. Think of the circuit breaker pattern as a safety switch for microservices. So here is how it works. Circuit breaker pattern operates in three states. One is closed state. In this state, the circuit breaker allows all requests to pass through. The system monitors for failures, and if failures reach a predefined threshold, the circuit breaker transitions to the open state. Next one is open. In this state, the circuit breaker prevents all requests from passing through. This allows the failing service time to recover without being overwhelmed by the new requests. After a predefined timeout period, the circuit breaker transitions to the half-open state. Half-open state. In this state, the circuit breaker allows a limited number of requests to pass through to test if the underlying service has recovered. If these requests are successful and meet the recovery criteria, the circuit breaker transitions back to the closed state. If failures continue, it transitions back to the open state. So, by implementing the circuit breaker pattern, systems can avoid excessive strain on failing components, improve resilience, and ensure that faults are isolated and managed effectively. This pattern is vital for enhancing the reliability and stability of microservices architectures, allowing systems to handle failures gracefully and maintain overall functionality. In this video, we are going to learn two-phase commit pattern in microservices. Imagine each microservice as a musician in a symphony playing in perfect harmony. What if one musician fails? In microservices, ensuring every service synchronizes during a transaction is vital for data integrity. The two-phase commit pattern is a powerful protocol to keep your systems in synchronize. The two-phase commit pattern offers a masterful solution to ensure that every part of your system stays in perfect synchronization, providing the consistency and reliability that your operations demand. So, what is the two-phase commit pattern? The two-phase commit pattern is a protocol used to achieve atomicity in distributed systems. It ensures that a transaction either completes successfully across all participating services or is entirely rolled back, maintaining data consistency. So, how does 2PC pattern work? 2PC pattern involves two phases. One is prepare phase and the other one is commit phase. Prepare phase, the coordinator, it's often a transaction manager, it sends a prepare request to all participating services, asking them to prepare for the transaction. Next, each participant performs the necessary operations and locks the required resources but doesn't commit the changes. Next, participants then respond to the coordinator with either a yes, it means prepared, or no, it means not prepared. Next, commit phase. If all participants respond with a yes, the coordinator sends a commit request instructing them to finalize the transaction. And next one, each participant then commits the changes and releases the resources. If any participant responds with no, the coordinator sends a rollback request to all participants, undoing any changes made during the prepare phase. So when we use 2PC pattern, 2PC pattern is suitable for scenarios where data consistency is critical and the cost of inconsistency is high. Examples include financial transactions, inventory management, and order processing systems. As a conclusion, the two-phase commit pattern is a powerful tool for ensuring data consistency in distributing systems. While it comes with some performance and complexity trade-offs, its ability to maintain atomic transactions across multiple services makes it an essential pattern for critical applications. By understanding and correctly implementing the 2PC pattern, developers can build reliable and consistent microservices architectures that handle complex transactional requirements. In this video, we are gonna talk about Decorator pattern in microservices. Decorator pattern in microservices is a structural design pattern that allows you to dynamically add or modify the behavior of a service or component without altering its original code. This pattern is especially useful in microservices architectures where you may want to add cross-cutting concerns to services without modifying the core logic. So let's take a look at some key concepts of Decorator pattern. One is component interface. This defines the interface or abstract class that the core service and all decorators will implement or extend. It ensures that the decorated service and the original service can be used interchangeably. The other one is concrete component. The original service or object that you want to extend. This component implements the component interface and provides the core functionality. So next one is Decorator. This is the general term for any class that implements the same interface as the original component and wraps the component to add or modify behavior. This term decorator can refer to both abstract idea of wrapping a component and the specific classes that do the wrapping. Next one is concrete decorators. This is a specific implementation of a decorator. A concrete decorator is an actual class that provides specific added behavior. It's a subtype of the more general decorator. Let's see how it works in microservices. First, cross-cutting concerns. Suppose you have a microservice that performs a critical business operation and you want to add logging, caching, and security checks around that operation. Instead of adding this logic directly to the service, you create decorators for each concern. So what are these? One is logging decorator. Logs input, output, and execution time. The other one is caching decorator. It caches the result of operation to avoid repeated work. The other one is security decorator. It checks if the user is authorized to perform the operation. So let's take a look at component interface. This is the interface that defines the methods that both the core service and its decorators must implement. It ensures that the original service and the decorated services are interchangeable. In the example, iPayment service interface serves as the component interface. It defines the process payment method that all services must implement. So let's take a look at concrete component. This is the original service or class that implements the component interface and provides the core functionality. In the example, the payment service class is the concrete component. It implements the iPayment service interface and contains the core logic for processing payments. Let's take a look at Decorator example. It's a class that implements the component interface and contains a reference to an instance of the component. It adds or modifies the behavior by wrapping the original component's methods with additional logic. So in the example, logging decorator class is decorator. It implements iPayment service and contain a reference to another iPayment service instance. Let's take a look at example 2. So if we take a look at security decorator, security decorator class is a decorator. It implements iPayment service and contains a reference to another iPayment service instance. So here is concrete decorator. These are specific implementation of decorators that add particular behavior to the service. Each concrete decorator wraps the original service or another decorator to modify or extend its behavior. In the example, both logging decorator and security decorator classes are decorators.
They implement iPayment service and contain a reference to another iPayment service instance. So let's take a look at composition of decorators. This refers to the process of layering multiple decorators to add or modify behaviors in a specific order. So first, creating the core service. So here is payment service is the core service that implements the basic functionality. Here an instance of payment service is created which represents the core component that will be decorated. So here we add security with a decorator here. Security decorator is a concrete decorator that adds security checks to the payment service. The security decorator wraps the payment service instance. This means that whenever secure service is called, it first performs the security checks defined in security decorator before delegating the actual payment processing to payment service. So here we have another composition of decorators. Here we add logging as another decorator here. So as you see, logging decorator is another concrete decorator that adds logging functionality. Here logging decorator wraps the secure service, which means that before processing a payment, it will log the details. After logging, it will then call the secure service, which itself will perform security checks before finally invoking the original payment system. Here is last, when logged secure service process payment details is called the following sequence of action happens. Here is payment details as a parameter, and we call this method, and the following sequence here logging, its logging decorator logs the payment processing action. Next, security check. The security decorator checks if the user is authorized to make the payment. And payment processing. If the security check passes, the actual payment service processes the payment. And next one, logging. After the payment is processed, the logging decorator logs the completion of the payment processing. In this video, we are going to learn cap theorem. Cap theorem is a principle that applies to distributed systems. So the theorem states that it is impossible for a distributed system to achieve all three of the following goals at the same time. These are consistency, availability, and partition tolerance. Let's see what are these. Consistency is every time you ask for data, you get the most recent version. Think of it like a book where every page is updated to reflect the latest information. Availability. The system is always responsive. If you ask for data, you will always get an answer, even if it is not the latest version. And partition tolerance. The system keeps working even if there is a network problem that splits the system into parts. It is like having a library that still operates even if the communication between its branches is interrupted. There are some trade-offs. These are consistency and availability. If you choose to prioritize both consistency and availability, the system might not handle network issues well.
So, consistency and partition tolerance. If you prioritize both consistency and partition tolerance, the system might not always be available. Availability and partition tolerance. If you prioritize both availability and partition tolerance, the system might not always provide the most recent data. If we take a look at example, think about you have a magic box that can either always give you the latest candy, this is consistency, and always give you a candy whenever you ask, its availability, or continue working even if the magic box gets split into two parts, partition tolerance. So you can only choose two out of these three features at once. In this video, we are going to learn the relationship between microservices and event-driven architecture. Microservices and event-driven architecture are two modern architectural patterns used in designing and implementing software systems. Here is an overview of each and how they relate. So, event-driven architecture is a software architecture paradigm that promotes the production, detection, consumption, and reaction to events. There are some key components of event-driven architecture. These are events. Events are significant occurrences or states within the system or the external environment. Examples include user actions, system notifications, or changes in data. Next one is event procedures and consumers. Components, these are components that generate events, are producers, while components that respond to events are consumers. This decoupling allows for asynchronous and scalable communication between components. So, next one is event broker. It acts as an intermediary for events, facilitating communication between producers and consumers. Popular examples include Kafka, RabbitMQ, and AWS SNS/SQS. So, there are some relationship between microservices and event-driven architecture. One is loosely coupling. Both architectures emphasize loose coupling between components. Microservices achieve this by separating functionality into independent services, while event-driven architecture achieves it by decoupling event procedures from consumers through asynchronous event communication. The other one is scalability. Both architectures support scalability. Microservices can scale individual services, and event-driven architecture allows for scalable event processing and handling. Next one is flexibility and agility. Together they enable flexibility and agility in system design and evolution. Microservices allow for independent development and deployment, while event-driven architecture enables asynchronous communication and dynamic reactions to events. And complexity. Introducing both microservices and event-driven architecture adds complexity to the system architecture and requires careful design and consideration of factors like event schema, consistency, and eventual consistency. So there are some use cases for event-driven architecture and microservices. One is IoT applications. Event-driven architecture can handle massive volumes of sensor data and trigger appropriate microservices for real-time analytics or actions. Next, e-commerce systems. Microservices can manage different aspects such as catalog, orders, payments, while event-driven architecture ensures seamless communication and event-driven updates such as order placed, payment processed. Next one is financial services. Microservices can handle different functionalities such as accounts, transactions, while event-driven architecture ensures auditability and compliance through event logging and processing. In conclusion, while microservices focus on decomposing applications into small, manageable services, event-driven architecture complements it by enabling asynchronous communication and dynamic reaction to events, resulting in more scalable, resilient, and agile systems. Integrating both can lead to robust, flexible architectures capable of meeting modern software development challenges. In this video, we are going to learn how to implement event-driven architecture in ASP.NET Core. So, event-driven architecture in ASP.NET Core is a design pattern in which decoupled components communicate with each other by producing and consuming events. This architecture is particularly useful for creating scalable and maintainable applications, as it allows different parts of the application to operate independently and react to changes or actions in other parts of the system. Here we have an event definition example. So on the code example, you see how to define event, which name is ordered placed event. So you are gonna define the events that will be used in your application. These are usually simple data transfer objects that contain the necessary information about the event. Here we have event publisher example. So you create a service that will publish events. This can be done using in-memory event dispatchers, message brokers like RabbitMQ, Kafka, or cloud-based services like Azure Event Grid. So if we take a look at code example, this is in-memory example. We have event publisher interface. It defines the publish method prototype, and there is in-memory event publisher class at the bottom. So it gets handlers as a define parameters, and it defines publish methods. So you call in publish method and it publishes events. Next, we create event handler. You define event handlers that will handle the events. Each handler should implement a specific interface and contain logic to process the events. So in our code example, we have event handler interface, and it has a function definition which name is handle. It gets the event type parameter, and at the bottom we have order placed event handler class. It inherits event handler interface, and there is a method body, handle methods body. So in the method body, it handles the event such as send confirmation, email, update inventory. In this part, we registers dependency injection services. So you register the event publisher and handlers in the dependency injection container. So as you see in the code, you register your services with the add singleton type and add transient type. Next we see how to publish events. You publish event from your application services or controllers when specific actions occur. So on the code example, we have an order service class and it gets iEvent publishers services as a dependency injection method. It's constructor injection, and at the bottom there is a place order method. In the place order method you create new order object and you send this as a parameter to the publish method. So we handle events. Event handler will automatically handle events when they are published. For example, the order placed event handler will process the order placed event and perform the necessary actions. How we use message brokers? For more robust and scalable solutions, consider using message brokers like RabbitMQ or Kafka. ASP.NET Core application can use libraries such as Mass Transit or Service Bus to integrate with these brokers. Here we have an example with Mass Transit. Mass Transit is a free open source service bus for .NET designed for building distributed applications using messaging patterns. It helps developers create loosely coupled applications by enabling them to communicate through asynchronous messages rather than direct method calls. So to install Mass Transit, we add .NET package or NuGet package which name is Mass Transit, and also we install Mass Transit with RabbitMQ with the second package here. On the left we have example with Mass Transit. There is a configuration method here. We add dependency injection service for Mass Transit. Here we have definition of consumer. So this setup allows you your ASP.NET Core application to publish and handle events in a decoupled manner, enabling better scalability and maintainability. So we have order placed event handler. It inherits iConsumer interface and it has consume method here. So when you call the consume method, it defines, it publish, it handles events in a decoupled manner. In this video we are going to learn the relationship between microservices and event sourcing. So microservices and event sourcing are two advanced architectural patterns used in designing and implementing complex distributed systems. Event sourcing is a pattern where the state of an application is determined by a sequence of events that are stored in an append-only manner. Instead of storing just the current state of the data, all changes to the state are stored as a series of events. There are some key concepts of an event sourcing. One is event. An event represents a discrete occurrence that affects the state of the application. Events are immutable, and once stored, they cannot be changed. Next one is event store. It's a database or storage mechanism that stores events in an append-only fashion. It maintains a historical record of all changes to the application state. Next one is event replay. It's the ability to rebuild the current state of an entity by replaying all the events that have affected it. This allows for auditing, debugging, and historical analysis of application state changes. Next one is CQRS. It's often used in conjunction with event sourcing. CQRS separates read and write operations, allowing for optimized querying of data and handling of commands that change state. There are some relationship between microservices and event sourcing. One is decoupling and scalability. Microservices architecture and event sourcing both promote decoupling and scalability. Microservices achieve decoupling through separate services, while event sourcing decouples data storage and processing through event logs. Next, state management. Event sourcing shifts the focus from traditional CRUD operations to creating changes as events. This aligns well with microservices, where each service can maintain its own event log and derive its current state from these events. Next one is complexity and consistency. Introducing event sourcing in microservices architectures adds complexity due to the need for managing event stores, ensuring eventual consistency, and handling distributed transactions. However, it also enables greater flexibility and scalability in handling business process and state changes. Next, auditability and debugging. Event sourcing provides a detailed history of state changes, which is beneficial for auditing and debugging distributed systems. In microservices, where multiple services interact asynchronously, event sourcing helps in maintaining a clear record of what happened and when. Let's take a look at use cases. One is financial systems, where auditability and accurate tracking of transactions are critical here. And e-commerce, it's managing complex order processes and inventory changes across multiple services. And next, collaboration applications. It's a tracking user interactions and state changes in real-time collaborative environments. In summary, while microservices architecture focuses on decomposing applications into small manageable services, event sourcing complements it by providing a robust mechanism for managing and storing changes in application state. Together, they enable scalable, resilient, and flexible architectures capable of meeting the demands of modern distributed systems. In this video, we are gonna talk about HashiCorp in microservices. So let's take a look at HashiCorp tools in microservices. In the world of microservices, managing complexity is key. With multiple services interacting, each with its own dependencies and configurations, you need tools that can handle these challenges effectively. That's where HashiCorp steps in, offering a suite of tools designed to make managing microservices architecture smoother and more efficient. So let's explore how some of HashiCorp's flagship tools, such as Consul, Vault, Nomad, and Terraform, these play a crucial role in building resilient and scalable microservices. First, let's take a look at Consul.
In a microservices architecture, services need a way to discover each other and communicate securely. Console is the go-to tool for service discovery, health checking, and configuration management. Service discovery Console automatically registers services and their locations in a central registry. This makes it easy for services to find each other without hard coding addresses. We have an example here. So service A wants to communicate with service B. So instead of hard coding service B's address, service A queries console, which provides the address dynamically. Next one is health checking. Console continuously monitors the health of services. If a service fails, console removes it from the registry, preventing other services from attempting to communicate with a broken service. Next one is configuration management. Console's key value store allows you to manage configuration data centrally. Services can retrieve their configurations dynamically, which is especially useful for features like feature toggles or environment specific settings. In microservices, security is paramount, especially when dealing with sensitive data like API keys, passwords, and certificates. Vault provides a robust solution for managing secrets and encrypting data. Let's take a look at these. One is secrets management. Vault stores secrets securely and dynamically generates secrets on demand. For instance, it can create database credentials that expire after a certain period, reducing the risk of credentials being compromised. So we have an example here. Service A requests access to a database. Vault generates temporary credentials with a short lifespan, providing them to Service A securely. Next one is encryption as a service. Vault offers encryption services, allowing microservices to encrypt and decrypt data without having to manage encryption key themselves. Next one is identity-based access. Vault integrates with identity systems to enforce access controls, ensuring that only authorized services or users can access specific secrets. Next topic is Nomad. So when managing multiple microservices, you need an orchestrator that can deploy and manage workloads efficiently. Nomad is a simple and flexible orchestration tool that can manage both containerized and non-containerized applications. Next one is multi-cloud deployment. Nomad can deploy workloads across multiple environments, including on-premises cloud or hybrid setups, making it a versatile choice for diverse infrastructures. We have an example here. So you have a microservice that needs to run in both AWS and an on-premises data center. Nomad can schedule and manage deployments across both environments seamlessly. Next one is horizontal scalability. Nomad ensures your services are distributed efficiently across available resources, scaling them horizontally as demand grows. Next one is declarative job specifications. With Nomad, you define job specifications in a declarative format, allowing you to describe the desired state of your microservices deployment. So next topic is Terraform. Managing infrastructure for microservices can be complex, especially as your architecture grows. Terraform simplifies this by allowing you to define infrastructure as code. So, infrastructure as code, with Terraform you can write configuration files that describe the desired state of your infrastructure. Terraform then automatically provisions and manages this infrastructure. We have an example here. This simple Terraform script provisions an AWS EC2 instance. For microservices, you can define everything from networking to load balancers and database clusters in code. Next one is modular infrastructure. Terraform allows you to break down your infrastructure into reusable modules, making it easier to manage and scale as your microservices architecture evolves. Next one is multi-provider support. Terraform supports multiple cloud providers, allowing you to manage hybrid or multi-cloud environments seamlessly. So how these tools work together in microservices? In a typical microservices architecture, you might use these HashiCorp tools together to achieve a fully automated and secure environment. First one is console managed service discovery, ensuring that services can find each other and communicate without hard-coded addresses. Next one is Vault secures all the secrets and sensitive data your services need, with fine-grained access controls and dynamic secrets generation. Next one is Nomad orchestrates the deployment and management of your services across different environments, scaling them as needed. Next one is Terraform provisions the underlying infrastructure, ensuring that your environment is consistent and repeatable. In this video, we are gonna talk about why do we use proxy in microservices architecture. So, in a microservices architecture, proxies play a crucial role in managing and facilitating communication between services. Here are some key reasons why proxies are used. One is service discovery. In a dynamic microservices environment, services may scale up or down, and their network locations might change. A proxy can interact with a service registry to dynamically discover service instances and route requests to the appropriate service. Next one is security. Proxies can enforce security policies by handling authentication, authorization, and encryption of communication between services. This centralizes security measures, making it easier to manage and maintain. Next, traffic routing and control. Proxies can manage traffic flow between services, including routing based on specific rules, rate limiting, or even introducing fault tolerance mechanisms like circuit breakers to prevent cascading failures. Next one is API gateway. A proxy can function as an API gateway, which serves as a single entry point for clients to interact with multiple microservices. The API gateway can handle cross-cutting concerns like request routing, caching, rate limiting, and transformations. Next one is logging and monitoring. Proxies can log requests and responses, providing valuable insights into service performance and helping with monitoring, debugging, and auditing. Next one is simplifying client interaction. Clients may not need to know about the complexity of the microservices architecture. A proxy can abstract this complexity,
presenting a simplified interface to the client while handling the routing and orchestration of requests behind the scenes. In this video, we are going to learn Microsoft Thai, how it makes easier to implement microservices and how to manage. Let's begin. Microsoft Thai is an open source project, so when you install and run the Microsoft Thai, so you are gonna have this here. The dashboard will be seen and you are gonna see the services, and you can navigate to your pages here. This can be Swagger UI or something else about the project. And here is the logs here. If there is an error, you can see errors here. So how does it work? Microsoft Thai is an open source project designed to simplify the development and deployment of microservices applications. It's a tool that helps developers manage and run multiple services locally, making it easier to develop, test, and debug distributed applications. There are some key features of Thai. One is service discovery. Thai provides automatic service discovery, allowing different microservices to find and communicate with each other easily. Next, local development. It helps manage the local environment for microservices, including service dependencies and configurations, so developers can test and debug applications as if they were running in production. Next, simplified configuration. Thai simplifies the configuration and deployment of microservices by using a single YAML file to define services, ports, and dependencies. And integrated dashboard in the Thai. So Thai includes a web-based dashboard to monitor the status and health of running services as mentioned before. Next, compatibility. It works with various technologies and platforms, including Docker, Kubernetes, and .NET applications, making it versatile for different development environments. So, if we take a look at basic structure of Thai, first you ensure you have a Thai YAML file in your project directory which defines your services. So this file is used by Thai to understand which services to run. If we take a look at services here, this section defines the individual services that Thai will manage. Each service can be a .NET application here, Docker container, or other types of executable files, projects. And here the name of the service, project here, path to the project file for a .NET service, and bindings here defines which port the service will listen on. Ingress defines here how external traffic is routed to your services. This is especially useful if you want to expose certain services to the outside world. So in the example here, this is the name of the service to which traffic should be routed, and here is the port on which the service should be accessible externally, and target the port on which the service is running internally.
So here is the service definition we mentioned before, and environment variables here. These are the configure environment specific settings for each service, and there are also configs and jobs definitions in the YAML file. These are define additional configuration and background tasks if needed. So how we install Microsoft I? Here, first you ensure that you install .NET SDK. The version should be .NET 5 or later. Next, you open the terminal or command prompt. So to install, you use this command in the command prompt, and you can check Thai version if it is installed correctly with this command. So you run the Thai with this command, and if you wanna run the Thai and open the dashboard, you can use this command. So sometimes it can be used by other services, the port number can be conflict. So to solve this problem, you can use this command and you can change the port number of Thai. Then you can access the dashboard as this, the new port number. In this video, we are going to learn what is API gateway and some core functionalities of API gateway. API gateway is a server that acts as an API front end, receiving API requests from clients and routing them to backend services. There are some core functionalities of an API gateway. One is routing. It means directing client requests to the appropriate microservices or backend services. Next, protocol translation. This means translating between web protocols and WebSockets, HTTP and gRPC. Next, load balancing. It means distributing incoming client requests to multiple instances of a service to ensure optimal performance. Next, authentication and authorization. It means validating users and ensuring they have permission to access the API. Next, monitoring and analytics. It's tracking API usage metrics and analytics such as request rates, latency, and traffic spikes. Next, caching. It's storing response data to improve performance by reducing the need for backend calls. And next, request shaping and rate limiting. It's managing traffic by limiting the number of requests clients can make to the backend. So, API gateways are commonly used in microservices architectures to handle a diverse set of responsibilities and simplifying the client-side code. They can also provide security benefits by hiding the internal structure of backend services and by enforcing security policies and practices centrally. In this video, we are going to implement Ocelot API Gateway. So, Ocelot is a lightweight API gateway for .NET platforms, which is designed to work with microservices architectures. Let's begin. First, we create Ocelot API Gateway project. let's give it a name, Ocelot gateway. When we make it Ocelot, only Ocelot, it uh, it gives error. It gives conflict error with the Ocelot NuGet package. So we give Ocelot gateway name. Remove this one and create. So our project is created. Next thing we need to do, we need to install Ocelot NuGet package. Come here, not here. We come manage NuGet packages. We find Ocelot. So we install this one, we choose project, click install. So it's installed, fine. Next thing, we are gonna create ocelot.json file. We are gonna use this for configuration. So we are gonna define routes here. This is gonna be our configuration file. So if we take a look at here, downstream path template, schema and downstream host ports create the internal microservice URL, which this request will be forwarded. And upstream path template is the URL that Ocelot will use to determine which downstream path template to use for a particular request from the client. And this upstream HTTP method determines whether its HTTP request will be get, post, put. Okay. Next thing we need to do, come to program CS and register Ocelot service. We are gonna builder at these lines here. So it recognizes the Ocelot. We get ocelot.json with this, and we send it builder configuration as a parameter. Alright, and next thing we are gonna define Ocelot middleware here. Alright, everything is fine. And next we are gonna create a new microservice. Its name will be product. It's gonna be web API project. Products. So next, and create. Alright, next thing, we are gonna add controller here to send request and get response. Controller, add controller, API controller it will be, and we are gonna choose this one. It's gonna create methods, Let's give it a name, products controller. Alright, create. Okay, it looks fine. Let's run this. Alright, our project is running and come out. So products Swagger come out. So we are gonna use this port. We need to set the endpoints in the Ocelot API gateway. So we come here. Okay, we come to configuration file. So this will be our downstream path, and we write everything. Our port will be this one because it changed, and we need to get the correct endpoint for here. Let's check it. When we run Ocelot gateway project, this screen comes out and we are going to use this port. Let's copy this and paste here. So everything looks fine. So we are gonna use this one, and next thing, let's test our project. Let's come to let's open up the Postman. We're gonna send the request. Alright, Postman is here. Let's change this port number, and we are gonna use this endpoint. Let's make a request. So it's successful. So everything is fine. What we did here, we used Ocelot API gateway endpoint, and we used products controllers method here, method name. So our Ocelot API gateway redirects all the requests and forward it to products microservices. As you know, products microservices endpoint is not this one. Its endpoint is here. So 5136, but here we used Ocelot API gateway endpoint. This is the feature of API gateway. It it routes the all the requests to the related microservice endpoint.
In this video, we are going to learn how to use Dockers and microservices together. Microservices and Docker are often used together to build and deploy scalable and modular applications. Docker containers provide a lightweight and consistent environment to package and run microservices independently. Here is a brief overview of how microservices and Docker work together. So, microservices architecture breaks down applications into smaller, independently deployable services that are focused on specific business capabilities. Each microservice typically runs in its own process and communicates with other services via APIs. Docker is a platform that enables you to package an application and its dependencies into a standardized unit called a container. Containers wrap up a piece of software in a complete file system that contains everything needed to run, such as code, runtime, system tools, libraries, etc. This ensures consistency across different environments such as development, testing, production, and simplifies deployment. When we use Docker with microservices, there are some essential points. One is containerization. Each microservice is packaged into its own Docker container. This container includes the microservice code, runtime, and any dependencies needed to run that service. Next one is isolation. Docker containers provide process isolation, which means each microservice runs independently of others. This isolation ensures that changes to one microservice do not impact others unless intentional. Next, scalability. Docker containers are lightweight and start quickly, making it easier to scale individual microservices based on demand. You can spin up multiple instances of a container to handle increased load for a specific microservice. Next one is deployment and development. So, Docker containers promote consistency between development, testing, and production environments. Developers can work on different microservices simultaneously without worrying about compatibility issues. Next one is orchestration. Tools like Docker Compose, Kubernetes, or Docker Swarm are commonly used for orchestrating microservices deployed via Docker containers. These tools manage container lifecycle such as deployment, scaling, monitoring, and help in maintaining the desired state of microservice architecture. There are some benefits of using Docker. One is modularity. Each microservice can be developed, deployed, and scaled independently. Next one is resource efficiency. Containers consume fewer resources compared to virtual machines. And consistency. Docker ensures that applications behave consistently across different environments. And deployment flexibility. Containers can be easily deployed on premises, in the cloud, or in hybrid environments. There are some challenges of using Docker with microservices. One is complexity. Managing a large number of microservices and containers can introduce complexity in monitoring, debugging, and orchestration. And networking. Microservices need to communicate efficiently and securely, which requires careful network design and management. Let's take a look at best practice. So, first one is single responsibility principle. Each microservice should have a clear and distinct purpose. And next one, container size. Keep containers lightweight and focused on specific tasks. And monitoring and logging. Implement robust monitoring and logging solutions for better visibility into microservices performance. And security. Apply container security best practices to protect microservices and their data. In summary, combining microservices with Docker provides a scalable, efficient, and flexible architecture for modern applications, enabling faster development cycles and improved deployment process. In this video, we are going to learn how to install Docker and use it in Visual Studio 2022. Before starting, let's go to Docker website and install Docker desktop on Windows. So we choose the first one, download it and install. So after installing, this screen is gonna come out, Docker desktop. We are gonna use Docker desktop in Visual Studio. And next, let's create a Docker project. It's gonna be web API, and let's give it a name and click next. So here we don't need this one, and we click enable container support, and container OS will be Linux, container build type will be Docker file. This will be checked, and this will be checked, and create next. So here our project is installed, and if we take a look at the Solution Explorer, we see Docker file here. It's automatically started build. Alright, let's take a look at this one. Here is our configuration file, is automatically created by Visual Studio. So our project will be run on the Docker server. What else we need to do? Let's run the project. As you see here, container Docker file. This project is not running on IaaS, Internet Information Service. It's running on Docker. So as you see, the web page comes out, it runs on Docker, our Swagger page here. Next, we are gonna add support for container orchestration. Here we come. What is support for container orchestration? In Visual Studio, adding support for container orchestrator streamlines these tasks by providing built-in tools and features that integrate with popular orchestrators like Kubernetes, Docker, Swarm, and Azure Kubernetes Service. This integration helps developers to focus more on coding and less on managing infrastructure, leading to increased productivity and more robust applications. We are going to take the advantage of this feature. So how we do that? We come here and add container orchestrator support here, Docker compose, OK, click OK, choose Linux. OK, it's created Docker compose file, and it's created Docker ignore and Docker compose YAML file. Here, as soon as the solution is saved, it builds the project under the container and creates a Docker image. All the commands execution can be seen in the output window when the solution is saved. So as we see here, it builds the project under the container and creates a Docker image.
Let's check Docker images on the command line. Let's right click here, open in terminals. Alright, so let's write it down, images, Docker images. As you see, our Docker images is seen here. These are created.
In this video, we are going to learn microservices and Kubernetes. Microservices and Kubernetes complement each other well, offering a powerful combination for building, deploying and managing scalable applications. Here is how microservices and Kubernetes work together. Microservices architecture breaks down applications into smaller, loosely coupled services that are independently deployable and scalable. So, each microservice typically focuses on a specific business capability and communicates with other services via APIs. Kubernetes is an open source container orchestration platform that automates the deployment, scaling, and management of containerized applications. It provides a framework for deploying and running applications using containers at scale across clusters of nodes. When we use Kubernetes with microservices, there are some highlights. One is container orchestration. So, Kubernetes manages the lifecycle of Docker or other container runtimes. It schedules containers onto nodes in a cluster, ensures their health, and manages scaling based on resource utilization and defined policies. Next, service discovery and load balancing. Kubernetes provides built-in mechanisms for service discovery via DNS and load balancing across microservice instances. This ensures that microservices can find and communicate with each other reliably. So, next one is scaling. Kubernetes enables horizontal scaling of microservices by adding or removing container instances based on traffic or resource demands. This elasticity allows applications to handle varying workloads efficiently. Next, configuration management. Kubernetes supports configuration management and allows you to define environment specific configurations for microservices using config maps and secrets. This helps in maintaining consistency across different deployment environments. Next one, deployment strategies. Kubernetes supports various deployment strategies such as rolling updates and blue-green deployments, which facilitate seamless updates and rollback mechanisms for microservices. And last one is monitoring and logging. Kubernetes integrates with monitoring and logging tools, providing insights into the performance and health of microservices deployed within the cluster. This visibility is crucial for troubleshooting and optimizing application performance. So, there are some benefits of using Kubernetes. One is scalability. Kubernetes automates scaling of microservices based on resource utilization and defined policies. Next one is resilience. Kubernetes manages container health, restarts failed containers, and maintains desired application state, ensuring high availability of microservices. Next one is flexibility. Kubernetes supports hybrid and multi-cloud deployments, allowing microservices to be deployed across different infrastructure environments. Next one is efficiency. Kubernetes optimizes resource utilization through efficient scheduling and orchestration of containers, maximizing infrastructure utilization. There are some challenges of using Kubernetes. One is complexity. Setting up and managing Kubernetes clusters can be complex, requiring expertise in cluster administration, networking, and security. Next one is learning curve. So, Kubernetes has a step learning curve for developers new to container orchestration concepts and Kubernetes specific terminology, and operational overhead. Operating Kubernetes clusters requires ongoing maintenance, monitoring, and upgrading to ensure stability and security. So, there are some best practices. One is containerization. Package each microservice into its own container for consistency and isolation. And deployment automation. Use Kubernetes manifests, YAML files, or Helm charts for declarative and version control deployment configurations. And observability. Implement logging, monitoring, and distributed tracing to gain insights into microservices behavior and performance. And security. Apply Kubernetes security best practices to protect container networks and cluster resources. In conclusion, Kubernetes provides a robust platform for deploying and managing microservices at scale, offering automation, scalability, and operational efficiency benefits. When combined with a well-architectured microservices approach, Kubernetes empowers teams to build resilient, scalable applications that can adapt to changing business requirements and operational demands. In this video, we are going to learn how to use Kubernetes with Visual Studio 2022 or ASP.NET Core project. So first of all, we need to download Docker Desktop for Windows because we need to use Docker. We need to containerize first our application, then we are gonna use Kubernetes. We assume that you downloaded this one and installed. After you install, this screen is gonna come out, Docker Desktop. So what we're gonna do here, we're gonna come to Kubernetes link here and we're gonna enable Kubernetes here. It's gonna take a while. We click on this and we apply restart. Okay, we say install and we wait. Alright, so we enabled Kubernetes here. Next thing we need to do, we open up the Visual Studio and we are gonna create Kubernetes web application, ASP.NET Core web application. Creating, let's give a name, next. So here we need to enable container support because first we need to containerize to use Kubernetes. So here everything looks fine. Create. Alright, so here our web application is created, and as you see, Docker is running here, Docker desktop. So next thing we need to add YAML files. Add YAML file, new item. We are gonna add
deployment.yaml. We are gonna add two files for configuration. We are gonna add these lines to the YAML file. So here we have name of deployment, and we have number of desired replicas and label selector to match pods, and label applies to pods. And next thing, we are gonna add service YAML. Right click, add new item. We are gonna add service.yaml. Our YAML is gonna include these lines here. So we have product app service. This is our name, service name. Here we have same name, product app, like deployment YAML file. So we next thing, we are gonna open terminal. We are gonna run kubectl command. So we are gonna use this kubectl here. Okay, kubectl is a command line tool used to interact with Kubernetes clusters. It allows you to deploy applications, inspect and manage cluster resources, and view logs. So here kubectl apply it applies a configuration file to create or update resources in the cluster. So let's run kubectl command. Alright, it's created. Next, we are gonna run kubectl for service.yaml. Alright, configuration file is created, and so let's check if it is created correctly. We use kubectl get pods command, enter. So as you see, we have product app deployment files here. Next, we are gonna run the application. Let's run it. And next, let's check if it is correctly deployed. We run this command. So as you see, deployment is successful. Here are deployment name, everything looks fine. So when we run our project, as you see, our application is running, and our Kubernetes is running. So by using these methods, we effectively verify whether our ASP.NET Core application is successfully running with a Kubernetes cluster.
In this video, we are going to learn Azure Microservices. Azure provides a robust platform for developing and deploying microservices. Here we have Azure Services, Azure Kubernetes Service, Azure Service Fabric, Azure Functions, Azure API Management, Azure DevOps, Azure Monitor, Azure Cosmos DB. Let's take a look at them one by one. So, Azure Kubernetes Service is a managed Kubernetes service that simplifies deploying, managing, and scaling containerized applications using Kubernetes on Azure. It supports the orchestration and deployment of microservices using containers. Azure Service Fabric is a distributed systems platform that makes it easy to package, deploy, and manage scalable and reliable microservices and containers. It provides comprehensive support for both stateful and stateless microservices. Next one is Azure Functions. Azure Functions is a serverless compute service that enables you to run event triggered code without having to explicitly provision or manage infrastructure. It is suitable for implementing microservices that respond to events or HTTP requests. Next one is Azure API Management. Azure API Management helps organizations publish APIs to external and internal developers to access data and services. It provides features like API Gateway, Developer Portal, and analytics, which are crucial for managing microservices APIs. Azure DevOps provides a suite of services for end-to-end software development and delivery, including CI/CD pipelines. It supports building, testing, and deploying microservices applications using various Azure services. Azure Monitor provides comprehensive monitoring capabilities for applications and infrastructure on Azure. It helps monitor the performance, availability, and health of microservices and their dependencies. And Azure Cosmos DB. Azure Cosmos DB is a globally distributed multimodal database service that supports NoSQL databases such as MongoDB, Cassandra, SQL, etc. It provides guaranteed low latency and high availability, making it suitable for microservices that require scalable and globally distributed data access. These services together provide a robust platform for building, deploying, and managing microservices on Azure, catering to different architectural patterns and scaling requirements. In this video, we are going to learn Azure microservices, how to install, how to use them. So, first of all, we go to portal.azure.com website, and it requires to enter with Microsoft account. When you sign in with your Microsoft account, then it redirects you to Azure main page. You see here many Azure services. We are gonna first create container registry by clicking on this icon, and this form opens up. So we fill out the form, and it's validating
the form, and when the validation passed, you click the create button at the bottom, and container registry will be created. Next, you will get your tenant ID. How you can get your tenant ID? You go to this website and intra.microsoft.com, and you click on overview, and when you click on, your tenant ID will appear on the page, and you copy this tenant ID and you enter this command az login tenant, and your tenant ID will come here, and you click on enter when you enter this command, and your subscription will appear here, your subscription info, and your subscription ID, tenant ID will appear here. So everything looks fine. So when you write this command az account show, your account information will appear here, so it's better to keep this information to use next time. Next thing, you go to Azure page again, and you click on the Kubernetes service, and this page will come, and you click on create a Kubernetes cluster button, and Kubernetes cluster form will come, and you fill out the form like this, and click review and create. Then you successfully deploy your Kubernetes cluster, and as you see, your deployment is complete successfully. Next, you go to command prompt and write down the following command. So when you write this command, the output includes credential that you must protect. Be sure you don't include these credentials in your code, or check the credentials into your source code. So you keep this information to use next time. And next thing, you go to command prompt and write down az acr login name microservice demo app. This command uses the Docker client to set a Microsoft Intra token in the Docker config file. Once you have logged in this way, your credentials are cached, and subsequent Docker commands in your session do not require a username or password. Next, you go to command prompt and write down the following command. So use kubectl get service command used to list all the services in a Kubernetes cluster. This command retrieves information about the services, such as their names, types, cluster IP, external IP. And next thing, you go to Azure page again and click on the Cloud Shell button, and terminal will start when you click on this. So you can write commands to the terminal. So next, you write down this command. This command is used to get access credentials for an Azure Kubernetes service cluster. This command merges the cluster's kube config file with your existing kube config file, allowing you to use kubectl to manage your AKS cluster. Next, you go to command prompt and write down these commands, and you see the result: kubectl get nodes. You see the nodes here, and use kubectl get paths and kubectl get all. You can use these commands and get information about your cluster. And next, you create a manifest file for applying web application. To do that, you go to terminal and write v space aks app.yaml command, and it's gonna open a new file, and you write down this config file in the aks app YAML file. So when you finish, you can press escape to switch from insert mode to command mode. To save file and exit, you type WQ and press enter. So to quit, you press Q. You use these commands. So when you are done, you can use these commands to check Kubernetes cluster are installed. So when you write ls command, you see your file. When you write kubectl apply, so your deployment files created, and you see your kubectl get deployments, list your deployments. So kubectl apply creates deployment by using your config file, and you can use kubectl get svc and kubectl get rs, kubectl get pods. You can use these commands by checking the result.
In this video, we are going to learn the relationship between microservices and serverless computing. Microservices and serverless computing are two architectural paradigms that have gained significant popularity in recent years, each offering distinct benefits and challenges. Serverless computing, often referred to as function as a service, it's a cloud computing execution model where the cloud provider manages the infrastructure and developers focus on writing functions that respond to events or triggers. There are some key characteristics of serverless computing. One is no server management. Developers do not need to provision, scale, or manage servers. The cloud provider handles infrastructure management, including scaling and availability. Next one is event driven. Functions are triggered by events such as HTTP requests, database changes, or message queue notifications. They are stateless and ephemeral, running only when triggered and scaling automatically. Next one is pay-per-use. Billing is based on the actual execution time and resources consumed by the functions, providing cost efficiency for applications with varying workloads. Next one is high scalability. Serverless platforms automatically scale functions in response to incoming requests or events, ensuring optimal performance without manual interventions. There are some relationship between microservices and serverless computing. One is complementary architectures. Microservices and serverless computing can be used together to achieve highly scalable, flexible, and cost-effective architectures. The other one is microservices as functions. In some cases, microservices can be implemented as serverless functions, especially for lightweight event-driven tasks or APIs. This approach leverages the scalability and cost efficiency of serverless computing while maintaining the benefits of microservices architecture for larger scale services. Next one is integration challenges. Integrating serverless functions into a microservices architecture requires careful consideration of communication patterns, data consistency, and operational monitoring. Tools like API gateways, event brokers, and service meshes can facilitate integration between microservices and serverless components. Next one is use case optimization. Serverless functions are well suited for tasks that benefit from event-driven ephemeral execution such as image processing, data transformation, or handling asynchronous events. Larger stateful microservices may benefit from traditional deployment models to maintain persistent state and long-running processes. If we take a look at use cases, one is batch processing. Serverless functions can handle periodic batch jobs or data processing tasks within a microservices ecosystem. Next one is event-driven workflows. Integrating serverless functions with microservices allows for dynamic response to events from external systems or user interactions. Next one is prototyping and experimentation. Serverless platforms enable rapid prototyping and experimentation with new features or functionalities without the overhead of infrastructure management. In conclusion, while microservices architecture focuses on decomposition and independent scalability of services, serverless computing complements it by providing on-demand execution of functions, automatic scaling, and cost efficiency. Together, they enable developers to build flexible, scalable, and responsive applications that meet the demands of modern cloud-native environments. In this video, we are going to learn security in microservices. Security in microservices is crucial due to the distributed and interconnected nature of these systems. Here we have some key considerations and practices to enhance security in microservices architecture. So let's take a look at authentication and authorization. First one is OAuth 2 and OpenID Connect. OAuth 2 and OpenID Connect are widely used standards for securing APIs and managing user authentication and authorization in modern applications, including microservices architectures. The other one is JSON Web Tokens, JWT. JSON Web Tokens are a compact URL-safe means of representing claims to be transferred between two parties. They are commonly used for securely transmitting information in a distributed environment, such as microservices, and for implementing authentication and authorization mechanisms. The other one is role-based access control or attribute-based access control. So, role-based access control is an approach to restricting system access to authorized users based on their roles within an organization. It simplifies management by grouping permissions into roles and then assigning users to those roles. Next one is API gateways. So, securing an API gateway is crucial in a microservices architecture as it serves as the entry point for all client requests to your services. Proper security measures ensure that the API gateway can protect the backend services from various threats and vulnerabilities. So, we use an API gateway to handle common security tasks such as rate limiting, authentication, and logging. It centralizes security policies and provides a single entry point for requests. Next one is service to service security. So one of the service to service security is mutual TLS, MTLS. Mutual TLS is an extension of the standard TLS, which means transport layer security protocol, that adds an additional layer of security by requiring both the client and server to authenticate each other. This is particularly useful in microservices architectures where secure communication between services is critical. So, in mutual TLS, you ensure secure communication between services. If we take a look at service mesh, it's a securing a service mesh is critical because it manages and controls the communication between microservices within a distributed application. Tools like Istio or Linkerd can manage service-to-service communication security, including MTLS, authorization, and monitoring. Next one is data protection. So, if we take a look at encryption, we encrypt data both in transit and at rest. We use TLS for data in transit and strong encryption algorithms for data at rest. And secrets management. We use secure vaults, for example HashiCorp Vault, to manage and access secrets, API keys, and credentials. HashiCorp Vault is a tool designed for securely managing secrets and protecting sensitive data. It provides a unified interface to access secrets across various environments and uses policies to enforce security. And next one is logging and monitoring. So centralized logging is aggregate logs from all services for better monitoring and incident response. Intrusion detection system, it monitors for unusual patterns or behaviors in network traffic. And network security. In network security there is network segmentation. Network segmentation is a crucial security practice that involves dividing a network into smaller, isolated segments to improve security and manageability. Each segment can be secured independently, reducing the attack surface and limiting the spread of potential breaches. And firewall rules. It applies strict firewall rules to control inbound and outbound traffic. And dependency management. We regularly update dependencies and use tools to scan for vulnerabilities. For example, sync OWASP dependency check. We avoid using outdated
or unsupported libraries and frameworks. Next one is container security. One is image scanning. We scan container images for vulnerabilities before deploying. Next one, runtime security. We use tools to monitor container behavior and detect anomalies, for example, Falco, Aqua Security, and least privilege. We run containers with the minimally required privileges. And security policies. We implement security policies as code, for example, Open Policy Agent, to ensure consistency and automate enforcement. And we regularly review and update security policies. And next, compliance and governance. We ensure compliance with relevant regulations, for example, GDPR, HIPAA, and we conduct regular security audits and assessments. Next one, incident response. We have an incident response plan in place to quickly respond to security breaches. We conduct regular drills and update the plan based on new threats and learnings. So, in conclusion, implementing these practices helps create a robust security posture for microservices-based architectures, mitigating risks and ensuring the integrity, confidentiality, and availability of the system. In this video, we are going to talk about implementing JSON Web Token. Imagine JWTs as a special passcode that allows users to access various parts of your app securely. This passcode is compact, URL safe, and contains all the necessary information to verify a user's identity and permissions. A JWT is divided into three parts. One is header. It contains metadata about the token, like the type JWT and the signing algorithm, for example HMAC. And next one is payload, holds the claims or data, such as user ID and roles. Next one is signature. It is a cryptographic signature created using the header, payload, and secret key. This ensures the token hasn't been tampered with. So here is how you can create a JWT. First, choose a library. Depending on your tech stack, pick a library from JWT handling. In .NET, here is the library name. Generate the token. Define claims. Specify what information you want to include in the token. Sign the token. Use a secret key to create a signature that ensures the token is secure. Here in the code block, first we create the instance. This instance is JWT security token handler. It manages JWT operations. Next line is here. Generates a byte array from the secret key string used for signing the JWT. Next code block here. Security token descriptor. It configures JWT. Claims here includes user details like name and role. Expiration sets the token to expire in 1 hour. Signing credentials uses the secret key and HMAC. SHA-256 algorithm for signing. Next one is token here. Token handler create token. It creates JWT based on the configuration. And next token string here serializes the JWT into a string format for use in authentication. Here we use JWT tokens. Send the token. After authentication, send the token to the client. The client should store this token and include it in the authorization header of requests. Here we use JWT tokens. Validate the token. On the server, decode and validate the token using the secret key to ensure it's valid and hasn't expired. Here we take a look at the code. What does it do? Here creates the instance to handle JWT validation. And next line here generates a byte array from the secret key string used for verifying the JWT signature. Here the principal validates the token, checks the token's issue signing key. Here checks the token signature using the provided key. And validate issuer skips checking the token's issuer here. It outputs here if the token is valid and returns a claim principal which contains the user claim such as roles, permission, etc. So there are some security best practices. First, use HTTPS. Always transmit tokens over HTTPS to prevent interception. Next, short expiry. Set short expiry times and refresh tokens periodically to minimize risks. Next, secure key storage. Keep your secret keys secure and rotate them regularly. JWT offers a secure and efficient way to handle authentication and authorization in modern applications. By generating, sending, and validating tokens, you can ensure that your app communicates securely and efficiently with its users. In this video, we are going to learn ABP framework. It stands for ASP.NET Boilerplate Framework. So we're gonna take a look at ABP Microservices project. So ABP framework provides a structured approach for building modern web applications and microservices. Its architecture is designed to support modularity, separation of concerns, and ease of maintenance, particularly in large-scale enterprise solutions. To use the full feature of ABP framework, you need to subscribe to a commercial plan. ABP Microservices project architecture typically includes several core concepts and components. One is microservices. In an ABP-based microservice architecture, the solution is divided into multiple microservices. Common microservices might include user service, which is manage user accounts, authentication and authorization. Order service handles order processing and management.
Product service manages product catalog and inventory. API gateway, it's an entry point for clients to interact with the microservices. It handles routing, load balancing, and sometimes authentication. Microservice project, individual project for each microservice. Each microservice project includes its own DB context, domain entities, and business logic. Shared library, a library containing shared components, utilities, and common code used across multiple microservices. When working with the ABP framework to build microservices, you typically follow a structured approach to create a scalable and maintainable solution. Here is a general structure of how you might set up an ABP microservices architecture project. In our solution, we have authentication server, gateways here, project. Here we have host administration service. We have identity service here. So these are our microservices. These are our microservices here. Identity product service, SaaS service. So DB migrator, when you run the project, it creates database and tables. So core components, entity framework core includes DB context. Each microservice has its own DB context for managing database interactions. And migrations, each microservice manages its own database schema using EF core migrations. ABP module systems. Modules, ABP uses a modular architecture where each microservice can be divided into modules. Modules contain domain logic, application services, and other related components. Module dependencies. Modules can have dependencies on other modules, which allows for reusability and separation of concerns. The other core component is application layer. Application services. Each microservice includes application services that encapsulate business logic and interact with domain entities. DTOs, these are data transfer objects. These are used to transfer data between services and layers. Domain layer. Entities. Domain entities represent the core business objects. Repositories. Repositories are used to access and manage domain entities. Infrastructure layer. In this, repositories implementation contains the implementation of repository interface. Data access, it manages database connections and transactions. API layer, controllers handle HTTP requests and route them to the application services. API contracts define the API endpoints and request response models. Microservices communicate using various methods. REST APIs. Each microservice exposes RESTful APIs for communication. Message queues. For asynchronous communication, microservices use message brokers.
Event bus. Distributed event bus systems are used for publishing and subscribing to domain events. Modular architecture. Purpose: enables separation of concerns and promotes reusability by organizing the application into distinct modules. Implementation: each microservices can be treated as a module with its own domain, application logic and API. CQRS. Purpose: separates the logic for reading and writing data. Implementation. Different handlers or services are used for query operations, read and command operations, right? Domain driven design. Purpose: focuses on the domain and its logic to create a model that accurately reflects the business requirements. Implementation: entities, aggregates and value objects represent the domain of concepts. Event driven architecture. Purpose: decoupled services and enables asynchronous communication. Implementation: services communicate via events which can be published to an event bus and handled by other services. Authentication and authorization. Purpose: manages user identity and permissions across services. Implementation: handled by the API gateway and identity server. Logging and monitoring. Purpose: provides visibility into the application's behavior and performance. Implementation: centralized logging and monitoring solutions. Cross-cutting concern configuration management. So purpose: manage application setting and feature toggles. How to implement centralized configuration services. Microservices can be deployed independently and scaled based on demand. Common deployment strategies include containers and orchestration. So, finally you did it. Congratulations. Thank you for joining and completing the Microservices online course. Your commitment and engagement throughout the course have been truly commendable. We hope that you found the course informative and that it has provided you with valuable insights and skills that you can apply in your work and personal projects. Your dedication to learning greatly contributed to a positive and enriching experience for everyone involved. As you move forward, please feel free to revisit the course materials and continue to engage with the resources provided. We encourage you to stay connected with your fellow participants through our discussion forums and future events. Your feedback is invaluable to us. Please take a few moments to complete the course evaluation survey, as it will help us improve future offerings. Once again, thank you for your participation and enthusiasm. We look forward to seeing you in future courses. Best regards.